Okay, welcome everyone. My name is Mikko Rapeli and this is my colleague Goulart. We are from BMW Car IT and we are here to present or talk about continuous integration and testing of a Yocto project-based automotive head unit. First of all, a few words about BMW Car IT. It was founded in 2001. It's a small subsidiary of BMW AG, and we are basically a software house inside BMW. We do products for the BMW products, as well as some research and also open source software project there. Of course, BMW makes cars, and in those cars, for example, this is an i8 hybrid engine car with carbon fiber chassis and whatnot. And inside the car, in the cockpit next to the driving wheel is the head unit with a big display. And here on the bottom left, you can see the display of the head unit showing the maps and navigation data for the driver. Usually the driver uses a simple round joystick and a bunch of buttons to control this display. And of course, this head unit is connected to the other buses in the car and uses various data from there to display and convenience features. Our product setup, basically to develop a head unit for BMW cars. Connected multimedia computer with navigation and telephony and other features. Several companies are involved, physically distributed in Germany and other countries. We have hundreds of developers at various levels of the software stack. Due to these multiple companies, also really complex IT and CI infrastructure, which means we have a few technical and partially also political obstacles when setting up technical solutions for various things. Requirements for our CI system, basically to provide fast feedback for developers, integrators, and project organization. Basically, multi-stage CI is the implementation, where the first phase is a software component change verification inside an SDK environment. Basically, we build the software components in the SDK and execute all the unit tests that are available. In the software integration for the whole system, we then do CI builds for the full system, for all targets, for all images, and then have some quality assurance checks around that, and then do actual on-target testing with the provided images, and then provide results to the CI system.
So to implement this build system, we use Yocto, which I'll go really quickly over this because it's kind of basic information about Yocto. But just for those of you who don't know Yocto, it's a Linux-based cross-compilation framework. It uses as sources metadata, which can be configuration files or recipes that implement tasks. It has a task scheduler, which is called bitbake, which consumes its inputs, the metadata, and generates as outputs packages, images, toolchains, SDKs, etc. One of the characteristics is performance of bitbake. It can be really fast, but it compiles a lot. So two of the main things for performances is the shared sysroots and the caching of bitbake. So we will see in the next slides that especially the sysroots, which is shared, can be a source of problems in our case. So some neat features and characteristics of Yocto. It's very flexible. We can basically do anything we want with it. We have very fine-grained control on the output artifacts. We have the possibility of configuring it in compile time, which we cannot easily do with package-based distributions. It's very extensible. We can add or extend it. It provides a very useful thing, which is license tracking. So we can specify what license we cannot ship, which is kind of crucial for legal reasons. And it has commercial and community support. Both of them are very good. And another neat thing is QA checks, which we extensively use to guarantee some basic quality on our projects. So some words on source code management. As Mikko said, we have some component builds and system builds. So this is about components. Basically, the source can come in these three types. We can have public open source sources, internal projects, internal to the company, and binary deliveries from suppliers. So it's usually in subversion, and it's really binary. We don't need to compile this. So here is the more complex, just some words here to give you a better idea what software components mean. For example, take BizBox. It's usually a single repository that you just fetch the source or the tarball and compile. And the system components is actually a little bit more elaborate. So we basically have Yocto project, some open source meta layers, some proprietary meta layers that we keep in the company. All these components are Git repositories, and we use submodules to manage them. So to have a revision in our repository or a version, we just tag the base repository with Git submodules. There are some drawbacks about using this approach. It can be a bit confusing for new developers coming to Git. Adding or removing submodules is a bit tricky to test in our CI infrastructure, and it's not nicely integrated to Gerrit, GitWeb, or Git tools. For example, repo, which we haven't tried yet in this project, has a much better integration to Gerrit, but unfortunately we don't use it. So we use Gerrit as a code review tool and server for Git repositories. We use the concept of topics to group many commits. So when we want to build a change is usually in a topic that can be composed by multiple commits. We have a custom tool to check out the topics into our local copy of the repositories, so we can easily test a topic, for example, in a local machine. CI jobs can verify changes with the same topic, and that's what we use for verification builds. A positive aspect of the use of Gerrit, it's quite straightforward for experienced developers. It works quite well if people know what they are doing. But it's a bit bad for developers with not a lot of experience. And so they make some mistakes like mixing unrelated changes in a single Git repository, for example, under the same topic. Usually that should not be like that. And for example, they could try to merge commits that are not part of the same branch too. Yeah, the UI is not very good. It's a bit confusing. And in our case, the Gerrit version that we are using is not really up to date. There are some alternatives like Patchwork, GitHub, GitLab, but we don't really use them. So about the source code change integration, for the component case, which is the simplest, it's very easy. It's just a normal Git workflow. We commit and merge changes. And the system integration is a little bit more complex because a single change can involve multiple repositories. So we have to create a topic, submit. It goes through a verification build, and it also goes to peer review. And once we get a positive review and a successful build, it goes through a board of managers that may approve or not this change. So only after this approval that we get the change integrated.
Okay, so then I'll explain in a few slides our CI pipeline. For the software component builds, like I said, we compile in the SDK, and the developers work with the SDK. Then the developers push their changes to Gerrit for code review, and their peers need to review the code with a +2. And then the Gerrit also triggers a verification builds within the SDK in our CI environment, which also executes unit tests. In case the verification is successful, the changes can be either automatically or manually merged into the base repo of the software component, usually the master branch. For the system integration, we have two types of integration requests, which are basically multi-Git tree pull requests. They can be automatically or manually submitted from a component repo when, for example, the master branch moves forward with a couple of new commits, and the only change that needs to be done is that the bit baker recipe has a new hash. For the more complex scenarios, we have a system integration Gerrit topic, which, for example, changes a number of bit baker recipes in a number of different meta layers to produce some new feature. And we bundle these into a one Gerrit topic and then verify and fix those, verify and review those. So the multi-stage CI comes from the SDK build, SDK verification for a single component, then complete system builds for system-wide changes, and also before releases we also tested that our merge was successful and didn't break anything. So here's our workflow. Developer with a software component, developer works with Git changes, pushes them to Gerrit, into Git, and that triggers an SDK verification build and unit test execution in the CI environment. And from this we get the verification results. And then we require that the developer's code changes are also reviewed, so there needs to be a +2 in Gerrit. If all of this is fine, then the changes can be merged back into the system, into the master branch of the software component. In the CI environment for the SDK builds, the SDKs come from actually released versions of our base system from BitBake. And we automatically update to the latest SDK in every CI instance. For the system change verifications, like I said, a single component can change into a new Git hash in the BitBake recipe, or a software integration works with a number of BitBake recipes and a number of layers and pushes these changes into Git in a single topic. This triggers a system build in the CI environment, which also executes the bug tests in the real target hardware environment. If all of this passes, there will be a verification +1 result in Gerrit review. And of course, we require that the integrators also do peer review, and there needs to be a +2 in Gerrit. If all of these are fine, the system allows the integrators to send an integration request, which is basically a pull request for multiple Git trees into the next stage. So in the system release stage, the input is the integration requests, basically changes in BitBake recipes or other stuff in the meta layers, also classes and so on. First, these changes go into a change control board, which is then under the control of our release managers, who then decide what kind of changes are now prioritized for today's release or tomorrow's release and so on. Then they bundle up a bunch of integration requests which are then merged into the base repository, and then this whole merge is again tested with the same system build or images, and also execute hardware and all other bug tests. If all is fine, results come back to the CI system, which automatically then publishes these results. It tags the base Git tree and publishes all build artifacts like images, SDKs, and caches, and so on. And the images, of course, go to the further stages of testing in our release process. As mentioned, the integration requests are applied and tested in a full system build. There's a change control board which can control what stuff goes in. And these integration requests are collected together and pushed out as a release, so daily. New releases can be created manually with the change control board, who select which stuff goes in and when, or automatically based on a timer. Every 4 hours, for example, comes out a release, and all integration requests are automatically accepted. But usually this is a bit tricky when you actually want to control what stuff goes into a release.
Okay, some words on our CI infrastructure. So as we mentioned already, it's based on Gerrit, Git, and some Subversion servers. We use Jenkins to orchestrate all the builds. We use mostly virtual machines. At the moment, we have 2 bare metal machines. They are quite powerful, as you can see in the numbers. And additionally to these CI builds, we have 1 daily or nightly build from scratch without BitBake's state cache. And we also have some minor services as file and cache servers, database, cluster, and issue trackers. Well, these slides are going to be available, so I'm not really going into details about the numbers, so you can quickly see them here and then take a look at these slides.
So then our test farm with, basically we have a test farm with special hardware, including the real target devices. We have a Jenkins master which takes in a new test candidate, whether it's a sort of build candidate or a release. Then it triggers or uses a Python-based test farm framework, which uses RapidMQ to handle all the requests to different executors. And basically we have 16 SDK and 20 virtual targets and 12 real target executors at the moment. These numbers are varying based on time and day and whether the machines are still alive. So besides the test time, we also have some automated tests for the build artifacts, just to do some checks as early as possible. For example, if the flashing tools are broken or missing from the release images, then we don't even try to put them into testing. Some statistics, here's a weekly statistics. So we run thousands of tests every week for different test targets. Unfortunately, I had to filter out some of the details, so these are not really interesting except to give an overview of how big our system is. Daily statistics, we work in Europe most of the time, so it's going to be German time frame and the office hours when the system is most busy. And the execution times that we have, the most time-consuming part in our case is the actual real target hardware test where the flashing takes quite a considerable amount of time. For virtual targets and SDK, which we also test, the execution times are much shorter. Some lessons learned from all of this. Keep it simple as you can. Use solid foundations. So we have had some hard lessons that we did not use some distributed system technologies, but tried to hack around with Jenkins and SSH and rsync and so on. And of course, one of the sad facts is if working in a company is that sometimes the corporate networks and the services provided there are not as reliable as, for example, GitHub. This is true for our current company, but also other companies that I've actually at least worked with. And also automate everything, including the server and system setup with Ansible and Puppet and so on. And virtualization, it might be a good idea for some IT managers, but it actually is not good for build performance in bit-baked environments. So positive aspects, we have done a system that works and that actually fulfills our requirements. It's a bit of pain sometimes to administer, and I also admit that also our users are sometimes quite loud and complaining that stuff doesn't work correctly. The negative aspects, like I mentioned, Jenkins isn't really a distributed system, even though it can trigger, you can trigger remotely a job on another Jenkins master, but that actually doesn't work quite reliably. And we haven't automated all bits and pieces, but we're working on that and trying to push everything into Ansible. And some changes in our CI infrastructure cannot actually be tested by the infrastructure or the CI jobs themselves. For example, rolling out new Jenkins versions or Jenkins module changes.
So some details about the builds. Well, for the software component builds, which are the simplest, we use SDK-based builds. So the SDK which is generated by the bit-baked build is used to build the component builds, the component software. So as an optimization, we use SIGCache in this case. So the system build is the most complex and the longest one. It runs inside an LXC container with Ubuntu 14.04. We do this because, as it's probably known, bit-baked is not really reliable when it comes to host contamination. We have some leaks into the build system. So we use the container to at least have a control on what may leak into our build. So with this, we can have some relatively control what goes into the final product, although we may have some leaks in the build system. And this container approach also allows developers to use whatever Linux distribution they want. And the container changes usually can be deployed faster than if we had to make some infrastructure changes. So for the implementation of this, we have a little wrapper around bit-baked, which is a shell script. It's just an implementation detail in this case, but we learned that we have to fail as early as we can, as lesson learned, and we should clean up stuff after we finish the process. So some numbers on the meta layers. We have a quite big scenario here for the build system. We have more than, actually these numbers are not really up to date. We have a little bit more than 60 meta layers, more than 2,800 recipes, and more than 400 BB appends for bit-baked. For the configuration of the build system, we use the stock localconf global configuration file for bit-baked. We have some sad magic to set some configuration variables. And differently from the stock bit-baked, we have a little script to determine the parallelization options for bit-baked. I'm going to talk a little bit more into details about this. So we have a single recipe, special recipe that we use to build everything. In this recipe, we have dependencies on other recipes that create about 9 images. These images include the flashing and testing tools, And we have some performance issues with the build of images because the generation of images cannot be really parallelized because the package manager, which is used to build up the image, is sequential. We cannot install packages in parallel. Although we can build images, we have 9, we can build images in parallel. Each image cannot be parallelized. We actually have some optimization with regard to the compression of images. We use PigZ for parallel compression. It's a parallel implementation of gzip. And our images are actually tarballs. They are not file system images. The flashing tools actually create the file system and deploy to the target correctly.
Okay, then a few words about our SDK. So we use a custom SDK instead of the Yocto upstream version. We do this in a bit different way. So our SDK mixes target and native SDK packages in a way that is actually really transparent to the users. The motivation is that developers have struggled with the cross-tool chain and the cross-environment setup and made mistakes in the CMake setup. In our way, the complexity of basically the cross-compilation setup is shifted from the developers to us integrators who manage the SDK. The SDK is also decoupled from the images, so we can have some stuff in the images which is actually not allowed for the developers to use, but for various reasons we need to provide it in the images. So we have a tighter control of the APIs that we expose to developers and urge them to use. We use a custom namespace tooling instead of a plain CH root to execute the environment of the SDK without root access. And basically, that means that when you are inside our SDK, normal commands like gcc make, out of tools cmake, and other, everything just works out of the box. From user's perspective, this is just a lightweight CH root environment. For the SDK, we have also tests for everything because we've noticed that even trivial changes or trivial tests find bugs, and trivial changes can trigger bugs. We don't use the Yocto upstream SDK tests. We have our own, but we are working on getting some collaboration done here. And these tests are also executed every time when we build an SDK in the CI system. We also have a Qt Creator-based IDE with a custom plugin to connect our SDK into the Qt Creator, so it's quite developer-friendly. And our SDK approach hasn't been upstream, but we're working on that as well. Then our SDK is actually the execution controller in our CI automated testing environment. So we deliver both the test controller and the thing that we test together into the system, and they automatically can be updated at the same time. And our iPackage archive, our package archive is format is iPackage, where we of course built a number of additional tools, debug symbols, and development packages which are not available in our SDK by default or in the images. Due to the complexity of our infrastructure with other multiple companies, we don't have a single iPackage repository server, unfortunately. But we do distribute these artifacts to different companies using various protocols and servers and whatnot. Some debug tools are only available in the package repository, for example, the GPL v3, and we can distribute it in the images. We don't at the moment support any incremental updates to the SDK or images because we can't provide a single package repo or package stream. And also, we unfortunately don't run a PR server at the moment, so we don't bump the version numbers of the packages in the binary packages automatically. We are planning to deploy that, but so far it hasn't been a huge issue for us. So as a feedback to the Yocto community, some difficulties that we are having with Yocto. Since our team is quite large and not many people are very experienced with Yocto, we have some difficulties with writing proper recipes. At the moment, our reference for quality in terms of recipes is the ones that we use from Pocky. Another major issue that we have is the shared sysroot approach that is used by Bitbake that can lead to many race conditions and issues with dependencies that may sometimes be available in the sysroot, sometimes not, depend on the parallelization of the tasks. So that leads to random build failures when the dependencies are not properly specified. We have many problems with this. In our case, mostly because of this issue with the shared sysroots, is that our builds are at the moment not reproducible. At least not if we use parallelization options. If we build sequentially, it would take forever,
but it would be reproducible, but that's not the case, that's not feasible in this case. Another issue that we have is that some developers actually use package managers from other languages like Java's Maven or JavaScript's NPM, and not properly integrated into Yocto. So they, for example, call NPM from a doConfigure or doCompile task, and NPM would download stuff from the internet, and that won't be properly cached, not properly verified by the Bitbake fetcher, and they may lead to build issues. And since it usually doesn't happen for the person who codes it, they just assume that it's fine and push the results, and it may even succeed in a verification build, but in random cases it breaks builds. Additionally, this way of doing things wrong, we don't get license tracking, which is quite important for us. So this is something that we have to address. And Bitbake sometimes rebuilds some dependents even when it's not strictly required. For example, when we are sure that ABI or API compatibility is preserved, but even if we change something in the recipe, Bitbake will recompile everything depending on the task which is affected, of course. And this leads to long build times. So here we have some numbers on the builds. This is per machine. We currently have 2 machines. So we have more than 22,000 Bitbake tasks, and these numbers that really go quickly over them. They will be available in the slides after that. So our build profile, our build may range from 20 minutes to 5 hours on those powerful machines that we showed. It depends on the caching, how much Bitbake is caching. The best case, it's 20 minutes. In the worst case, 5 hours. In our experience, build performance can be quite hard to optimize. There are countless variables to tweak in the build, including hardware variables, system variables, Bitbake variables. So it's really hard to optimize. And in our case, we have some quite heavyweight components, C++ based, that are really interdependent. So we change one, we have to recompile a lot of things. And still about performance, in our build profile, we have some 9 images at the moment, and they are not parallelizable. So the generation of these images can be a little bit time consuming. To help to analyze the profile of our build, the build stats data as generated by Bitbake has been very useful. So after the build is done, we still have some post-processing steps, which is basically checking the presence of the expected files. In case of a release, we have to prepare the S-state cache as generated by Bitbake to feed the next builds. Pushing artifacts like packages, images, SDK logs, etc. And well, as I mentioned, after a release, a new SDK is deployed into the system, so we can build software components using the new SDK based on the previous release.
Okay, then some optimizations that we have done. First of all, regarding the build performance. So first of all, you need to measure certain aspects of your build slaves, for example. The basic things are CPU usage, memory usage, disk usage, or local I/O, and network I/O. What we have found useful is to use Performance Copilot and its tooling for that. You can quite easily see what is the CPU utilization in a parallel or with multiple CPUs, and is the memory effectively used, or is everything going down through disk access and I/O, or even to network. We also have a download cache where we have a separate build job which runs a Bitbake build with the task fetch all, and that populates a download cache for us, and this is exported with an NFS to all our build slaves. This does not fully validate that the downloads are okay after fetch all. I mean, the compilations, or there might be some download might have failed and the system might have not noticed it, or it doesn't also notice that if something is actually wrong in the setup. So sometimes we have had corrupted downloads that have led to build failures in the build farm, and that's really tricky to debug. And ideally, of course, we would like to run all builds in an offline mode and with no network access in Bitbake and so on, but unfortunately this hasn't been the case in our environment, at least not yet.
So about the parallelization settings of BitBake. BitBake currently has two main variables to customize in case we want to tweak the parallelization. It uses two variables, BB number of threads and parallel make. Both of them by default are set to the number of CPU cores. In our particular case, it doesn't scale very well because, as we mentioned, we have some quite heavy C++ based components that take a lot of memory to compile. So in our case, for example, we have builders with 16 CPU cores. If we multiply BB number of threads and parallel make, we have, in the worst case, 256 compilation tasks running at the same time. That can be quite heavy if we are running C++ compilers. So what actually happened is that some builds just crashed because of they ran out of memory. So as lessons learned, we had to measure and set resource limits for BitBake tasks. That's currently not implemented, but ideally it could be implemented with C groups. So we could crash the specific task that is causing the out of memory error. Ideally, the BitBake scheduler should take into account the system load when it's scheduling new task. It doesn't happen. So if the system is completely trashed, BitBake will happily schedule new tests, even if they are compilation tasks. And as I mentioned before, optimal parallelization is very hard to get. For example, the builds depend, what we build depend on what's cached. So when we have lots of caching, high parallelization is desired. When we have low caching, so we have a lot of compilation, low or less parallelization is desirable. So what we've done, and we mentioned before, is we use a custom script that instead of using just the number of CPU cores as input, we also take the available memory as input. Here's the basic logic of this script. It will be available for you to take a look in the slides after that.
Okay, then we have tuned our build slaves a bit. So basically what we want to do is to avoid disk I/O as long as possible. That means that our BitBake builds basically run with ARM work enabled. So that means that any task when it's executed and the state data is no longer needed, BitBake will clean up the workspace for that. Here is some syscontrol settings for Linux to tune the VM values so that the writes to I/O are avoided. You can also go into details later on. And also basically we want to avoid swapping as much as possible. And lots of RAM help up to a certain point, but for example, on our machines, we tried to upgrade from 64 gigabytes of RAM to 128 gigabytes of RAM with 40 CPU cores, and build times did not improve at all. So more aggressive parallelization options easily lead to system trashing and thus actually slower builds. So our solution has been basically to try to experiment with our build profile and tune the parameters and actually measure the results. Then we have some quality assurance and security stuff that we also do in our system. We have static code analysis using CodeSonar. It basically uses shared programming rules and checks for these errors in the code. Basically finds memory leaks, buffer overflows, and race conditions, and so on. It's basically similar to what Coverity does, if you're familiar with that. All of our BitBake recipes are compiled using CodeSonar compiler wrapper. This is slow. We cannot do incremental builds at the moment. And it takes roughly 5 days to execute, so we do it basically weekly. It's completely automated, but we cannot integrate it easily into the CI workflow. But we provide these repos, for example, every week. Then we do open source license compliance checking. Basically, we use the license information provided by the BitBake recipes, but additionally, we also have black ducks tooling for this, and we analyze the source code for license violations. This, again, is also automated, but not directly connected to the CI workflow. Also, we're interested in security vulnerability analysis tooling. We've seen the patches floating around in the Yocto Open Embedded Core mailing list and tried them out, and they seem promising, but we're also looking into Black Duck because it provides similar features, and we already have the tool.
So now we are going to the conclusions on Yocto Project, which is our main tool to build our software. In our experience, the community support is excellent. Mailing lists, IRC, bug tracker is very good. The documentation is also very good, but the system is very complex. It's not easy. As we mentioned before, the layers provided by Yocto are reference in terms of quality. it's very difficult for us to reach the same level of quality as Yocto Project's layers. And we also have some problems, most of them due to the design decisions made for bitbake. The shared sys routes leads to race conditions and dependency issues in our builds. Bitbake in Yocto in general has a huge amount of global and mutable variables that are changed all along the build. In our case, we don't have reproducible builds. That's something we are working on to achieve in the near future.
Okay, some lessons learned about the whole CI setup. Basically, CI systems can be used to automate every task or required in the software development process. CI system builds find bugs, even testing, even if trivial, will find bugs, and that's really good. And cultural change is required, so we work in the automotive environment, and some developers and product partners actually appreciate the fast feedback that the system provides. Unfortunately, some don't. Some don't like that their code and bad code is published, and they get the penalty right away. Then quality of service, like I mentioned in the corporate networks, can make some CI setups really difficult. This is because of reliability is mostly chained. This means, for example, you have a source code server with 5% failure rate, for example, due to network issues or whatever, or a build reliability due to the mentioned fact in the bitbake, for example, of 10%, and that you have some instability in your testing, maybe hardware related and so on, and you have 10% failure rate there. And if you count these all together by multiplying the values, you will find a 23% failure rate, even though you haven't changed anything in your system. And that's something that our users are, of course, complaining about with this happens a lot. And if you do, the more stuff you do in your CI system, the more variables we will have, and all of this adds to instability. But on the other hand, the system actually does work. So that was our presentations. Would you have any questions to us? Go ahead.
There are many difficulties in your project.
Yep.
Why do you choose the project in your?
That's a good question. So the question is, why did we choose Yocto Project? I think it's because of our partners, the suppliers in the automotive domain were familiar with Yocto and basically provided the platform with support. So we use commercial support from our supplier for Yocto. That doesn't mean that sometimes all issues are fixed in their supplies, but we also do that, interact with them.
And we are open to suggestions on something better, because in our experience, and as far as we know, we don't know any better tool for this task.
Yeah. And as a personal note, I've been checking out the Debian-based discussions here. Yeah, go ahead. We have hundreds. So exact numbers I don't even know, because some of them are hidden behind other companies, but we have hundreds of developers working on the system. We don't have hundreds of developers working on the bitbake system, but overall we have hundreds of developers.
My question was, how big is the team?
Okay, how big is the team that set this whole thing up? We started off with a few developers working on the bitbake environment and SDK. Then it grew up. At the moment we have 10 people team, but these are also used as an experts in integrating whatever needs to be integrated into the system. So they are consultants in the whole project. Then we have infrastructure team. I think it also was one person doing it initially, ramped up to now I think 5 persons. Then we have a whole team maintaining the test infrastructure, test automation stuff, and I think there's more than 10 people at the moment working on that. So these teams are quite big, but on the other hand, we can get in 2 hours all of these results back in the project.
How many contributions achieved in the system in CI per day?
Per day. At the moment, there is a bit of a limit with the integration. So it's a bit difficult to count. So in the Yocto world, we can quite easily count how many Git commits are coming in, but it's not difficult, or it's a bit more difficult to determine how many changes happened in the software component trees, for example. At the moment, I would say that we are working on 2 to 3 releases a day to the system, and each release would contain, I would say, at least 10 integration requests, which are some kind of features implemented in the whole system.
Yeah, but those are changes related to the layers, not to the software components.
Yeah.
So the software component change may be 100.
Okay. Next question.
Which Yocto version are you using?
Jethro.
Jethro. And then your automated testing, does it include GUI testing or audio testing or anything beyond?
So we have multiple levels of testing. So the testing that we use in the tightest and fastest CI chain does not include anything but the target hardware and an SSH connection to the target hardware. So all additional hardware is in the further stages of testing, which we also have automated, but it doesn't happen inside the CI loop. There.
I'd like to know two questions. I'd like to know how your project relates to AGL and Genevieve, because there are many similarities on the, I don't talk about politics, but only technical stuff. At AGL, we have also built problems and built performance issues. For example, I wanted to try to use Ccache, because we know that feedback is a little bit picky on dependency. As you said, you finish up by rebuilding everything just because a single public cannot change, but in fact, the workload didn't change.
Yeah, so I guess the first question is how does it relate to Genevieve? This is a BMW product, and BMW is quite heavily involved in Genevieve. So we have a number of software components from the Genevieve work in our system. That's one thing. Second question was about using Ccache and other build performance enhancements. So we use at the moment state cache heavily. Ccache would be nice to have in some environments, especially where you can easily store it. Transmitting or transferring complete Ccache of the whole Yocto build into some machine and distributing it across machines, that is, I guess, way too heavy for anything. But if you have a local team-specific build server where usually just a couple of components are built, then using a local build slave specific Ccache would be nice, but unfortunately Yocto doesn't officially support it at the moment. Yeah, exactly. Okay.
For regarding your process, who's developing these integration tests? Are they coming from the, let's say, developers, the agile teams, or do you have a separate team?
Yeah, so we have a team who builds the test infrastructure, builds the test frameworks, for example. They do write some tests as an examples, but in theory, the people and developers of an individual component should write tests for that component. Also, this integration testing. So they should write the unit test, and they should write the sort of test that you would run on a target hardware when your component is updated there, that its interfaces are up and running. Unfortunately, this isn't always true, and the quality level of different developers varies a lot, and that causes problems then in the CI, of course. There.
You said that when you release the entire system, you have some post-process phase where you have to prepare the caches.
Yep.
What do you mean exactly?
So
How do you use them?
As far as I remember, we use state cache mirroring technique. So we prepare a state cache mirror. I think there's some symlink, hardlink magic involved in that. I can't remember any of the details.
Basically just store them.
Yeah, we store them. Yeah, exactly.
Yeah, basically we use the output of a release as input for the compilations after the release.
Another system is, you said there are some plans for upstreaming something. If I get it right, the first probably your SDK. How do you think this can fit inside the actual SDK concept?
Of Yocto. Oh, so the question is how does our SDK work with the Yocto SDK? I think it could be an alternative. So our SDK is honestly a bit too easy to use. We've seen quite a bit of software components where they actually have hard-coded path and so on. And we don't, actually then writing the bit-baked recipe for the stuff which was compiled in the SDK becomes really difficult if you find that someone just hard-coded the path of user lib include or user lib or user include. What I would like to have is that our SDK would export CC and LD flags and so on environment variables, but we don't do that at the moment. So I see it as an alternative to Yocto. We could discuss it, and we've been actually maintaining it across multiple Yocto releases already. So yeah, we'll see. There.
Do you have some recommendation on this problem of Yocto rebuilding the whole chain of dependencies? You know, when it starts, just rebuild everything.
Okay, so question is how to maybe prevent Yocto from rebuilding everything.
Or if you have something very
So I'll just let you know on how we're thinking of this could be solved. So we could run, there is an open source API checker toolchain which could be used to verify that, for example, a library did not break its API. And that tool would be used to detect that, for example, now there's no need to trigger any more builds. It's fine that this library was compiled alone. It's still compatible.
But it's not part of the big.
It's not part, so it's an open source tool. We have some proof of concept hacks where we try to see if this can be done. And for example, our SDK has this tooling also integrated so developers could use it. But now the big thing would be to hook it into BitBake somehow.
Yeah, and a smarter use of state cache could help too. If you merge several state caches into a single one, it could help, but it's kind of a lot of work to do.
Yeah. Yes?
Your SDK is rather big, so do you see that developers update this regularly, and do you help them? Is it a big chunk, or is it package-based?
So the question is how our SDK is big and how do we update it, or how developers update it. It is true that our SDK is big and not many components actually change that often in the SDK. Unfortunately, we've had some problems distributing or providing a single package repository, so we can't easily provide updates to them, to developers. Our SDK is big, but on the other hand, I think there was some there also on the slides that we are able to, in the CI system, and also developers can extend nowadays their SDK environment for their packages if they want to try something out or install debug symbols and some additional tooling. It is possible, but it requires some manual work. In the CI system, it's actually automatic, and also in the test environment, we actually install our target images, for example. They don't have anything except SSH enabled. All the other stuff comes from the SDK and is installed on demand to the target to, for example, enable some testing. So if the test requires special tooling on the target, it's not actually in the images, and we just install these when preparing for the testing on demand. Not a good answer maybe, but yeah, I cannot answer any better. Yes?
When you run unit tests, how do you run unit tests?
I think, how do we run unit test was the question. So I think we run mostly Google test and those based. G-test-based testing, unit test. That's what we recommend. We don't actually care how the developers do that, but we expect that there will be a make test, basically, in their build chain. And this can be configured.
Do you run it on native or in
We run it in the SDK environment, in which in our case mixes both target and native binaries. So it's running with the real compiled targets. And that requires that if the execution environment for the target is different from your architecture that the build servers are running, then QEMU is involved.
We have a question here.
You talked about reliability, 76%. Does it mean that around 25% of the time the infrastructure is down, or does it mean that 1 out of 4 integration requests are failing because...
It means that so the question was about a reliability example. So this wasn't a real example. I think we are a bit better in reality, but it's just an example. If you connect unreliable things into a chain, the whole throughput of the chain will be multiplication of those unreliabilities. And that means that every single CI execution, whether it's a topic built from a developer with a Gerrit topic, whether it's a release candidate, will have failures with that percentage. For example, this 23% in that example. So in many cases, you need to re-trigger things because of various reasons. And the more stuff you have in the chain, and if they are not always 99999% reliable, then you will be in a bit of trouble. Okay, yes?
As you pointed out, reproducibility is a problem, and you listed some of the reasons. Do you ever check? Do you use to say, at the moment, this is not a reproducible read? Do you test this and now the test is failing?
It's fundamentally, it's fundamentally broken, let's put it this way, because BitBake doesn't guarantee that, because it pretty much depends on the parallelization options and how things are parallelized. So if you build a software that depends on another one, and if that one happened to be compiled before and you don't have a proper specification of dependencies, this can build to and reproducible builds.
One comment to that. So the most visible way that our unreproducible builds are visible in our setup is that CI system is fine. It's great, everything builds. But the developer who tries to build, he doesn't have maybe the same download cache or state cache and tries to build something and it fails. He sees a clear bug somewhere. And that's really annoying.
Okay. Did you try that with the next one, Crowbot, which brings in the Uni-native?
Unfortunately, not yet.
Okay.
Yeah.
Because that should, well, of course, that should unify the state caches as it provides a unified shim layer.
Okay, so there was a suggestion to try Krogoth and hope that things are better there. Okay.
Yeah, one of the approaches we are trying to implement is the per recipe state cache. That's actually a file bug in the Yocto bug tracker about this.
Yeah. Okay.
Just comment to the Uni-native, so it will still not help you if your dependencies are missing.
Yep.
Nothing will help that.
Yep, exactly. So.
Except fixing the dependencies.
Exactly, that's true. But it's somehow easy for developers to introduce these kind of issues and ignore it.
There's
Yeah.
definitely benefits of using Uni-native, as you can you can make use of the native state for everyone.
Okay.
And another thing that you also should look at in Crowbot is the extensible SDK, which is
Yep.
way better than the
Yeah.
SDK in Yocto.
For sure, for sure. Okay, if there are no questions. Oh, there are still some questions. Okay, go ahead.
So, you talk about this is for a new product for BMW. So how old is this whole monster?
How old is our Monster CI setup? It's actually, I would say, more than 3 years old, and we've been jumping through different Jethro or Pokey versions and using different prototype environments. So this has been ramped over the years already. So we quite know how it works. And for sure, we would like to upstream many of the solutions that we have developed, many things, yeah.
Have you shipped your first project using?
And no, we have had sort of prototype products which prove, for example, when selecting the right hardware for our product. We've had the same setup already running with the prototypes from various vendors, basically boards. Yes?
Maybe to conclude, today you shared your experience, which is very interesting. I wanted to know if there is a place, a public place where you can share something, scripts or something.
I mean, we are active, so the question is how can we share or how you can maybe contact us. There's an email address over there. We are also actively on the Yocto and Open Embedded Core mailing list. Some of our guys are sending patches whenever we can. Unfortunately, we do have some time pressure to actually finish the product. So we can't always work on the open source stuff and push stuff upstream, but we try. We're also on the IRC channels, also asking questions, and we luckily get really good answers there. So we're there in the community.
Is this all based in Munich or Accenture?
Actually, we come from Ulm.
Oh,
Ulm. So, but it's the whole project is distributed in Germany and other countries. Okay, I think time is running out, so thanks a lot.